A very good afternoon to all present here. It gives me an immense pleasure to introduce Mr. Ravi Sundaram to our audiences, as well as the students or research scholars who have joined us on this Google Meet platform. So, sir, a very good afternoon.
Good
Next,
afternoon, all of you.
sir, a brief about the concerned or resource person. Mr. Ravi Sundaram is a founder director of Cengrs Geotechnica Private Limited, and he directs the company's geotechnical consultancy services and geotechnical construction activities. Talking about his career, he started his career with McClelland Engineers USA and worked at the company's office at Saudi Arabia, Qatar, and UK. His main or major expertise includes geotechnical investigations, geophysical surveys, ground improvement, and groundwater studies. He has been involved in developing engineering solutions to problems of foundations under the artesian conditions, collapsible dune sands, soft clays, expansive soils, etc. His special interests include foundations for tall buildings, thermal and solar power plants, and bridge foundations as well. Additionally, testing of pile foundations and strengthening the weak or distressed foundations. Next, coming to his publications or research work, he has published over 60 papers reflecting his experience in geotechnical practice. He strives to integrate field experience with academic research in order to be responsive to complex geotechnical challenges facing India. He even received IGS Professor Dinesh Mohan Memorial Award 2017-18 for the excellence in professional practice and delivered the prestigious 6th Madhya Culture in your International Society for Soil Mechanics and your Geotechnical Engineering in 2017 on the topic Geotechnical Investigations in Difficult Soil Conditions, Indian Experiences. Furthermore, he also received the IGS Delhi Lifetime Achievement Award in year 2012. He is also a prestigious member of BIS and IRC code committees. Not completed at this point, he even published a book titled Retrieving the Lost Paradise, Celebrating the Earth Day, Northern Book Center at Delhi in 2001. He even co-edited a book titled Geotechnics for Transportation Infrastructure, published by Springer Nature, Singapore, 2019. That's enough. And now I handed over the session to our session expert to deliver talk on the topic Forensic Geotechnics, Concepts and the Case Studies related to the session. And one more announcement. During the session, if you have any kind of questions or queries, you can put the same in the chat box, or you may ask the end or at the end of the session by unmuting yourself. Your questions or queries will be taken care by the expert at the end of this session. Till then, it's a humble request. Please keep yourself muted and your video should also be turned off. Over to you, sir.
Thank you very much, Mani. Very flattering introduction. I'm really grateful to you. I now start this presentation. Okay, so I am going to present today on forensic geotechnics, concepts and case studies. The word forensic, the dictionary meaning is connected to scientific tests used by the police to solve a crime. So obviously the word forensic has a legal connotation. The word is of Latin origin. It means offer before the forum. In ancient times, criminal charge was presented and argued before a forum of noblemen or public individuals. So that is the origin of this word forensic. This presupposes that a failure has occurred, resulting in some casualties, maybe loss of property, loss of human life, inconvenience to public, or breach of contract conditions, etc. And somebody has been blamed for it, the matter has gone into court or arbitration. Now, one step before we try to solve the problem before it gets out of hand, predict or not failure is likely to be taking place, and take required corrective action so that the failure doesn't occur, or if the failure has already occurred, try to fix the problem. So the forensic geotechnical engineer should apply the science and engineering rules within the rules and practice of the legal system effectively in presenting facts and resolving conflicts. He may act as a policeman or a detective trying to figure out exactly what happened, who is responsible. So you help the owner to find out what the problem was and who did it. You may provide technical inputs in an arbitration case, or may give expert opinion in a court case. On the other hand, he may be a friend. He can provide guidance in restoring the foundation and resolve the potential problem. Make sure that you are able to avoid litigation or arbitration. Okay. So the forensic geotechnical engineer should apply the science and engineering within the rules of and practice of the legal system to effectively present the facts and resolve the conflicts. So as I told you, you may act as a policeman or a detective to help the help the owner find out the problem, who's responsible, or he could be a friend. Forensic geotechnical engineering obviously involves identifying the problem, investigate the root cause, assess the risk, review the structural and geotechnical data, structural details, geotechnical data, predict your foundation behavior, perform a back analysis if the data is available, identify the causes of failure and risk. So forensics basically involves examining the evidence and trying to figure out exactly what happened, and then you could develop technically feasible solutions, review merits and demerits, select the final solution, implement and monitor that solution, and mitigate foundation distress. To resolve the disputes, the forensic geotechnical engineer should collect data related to the failure, characterize the problem, develop failure hypothesis, perform a realistic back analysis. That's the most critical thing. Record field observations and if feasible, monitor the performance. Quality control of technical aspects of the work has to be done. Since data is usually never completely available, the geotechnical engineer has to interpolate between limited data and make assumptions for the analysis. So therefore, he has to rely on sound engineering judgment. That's the key word here, sound engineering judgment. Forensic geotechnics is as much an art as it is a science. Today morning, Professor Madhya must have talked about geotechnical engineering is an art, but it's science, but it's a practice is an art. As far as forensics is concerned, the art and science merge together. So this is the forensic flow chart. You have a project here. There is a problem of inadequate foundation or excessive settlement. You review the structural details. You look at the geotechnical data, perform your analysis and predict the foundation behavior, find out what happened, why it failed, and then you come up with solutions. What are the alternate schemes? Review the merits and demerits of each scheme, recommend the final scheme, and then we have to implement it so that your project remains safe and sound. Identifying the root cause. This is the most critical thing. When there is a distress, it could be foundation distress or a structural distress. As far as the geoprofessional is concerned, he has to act as a doctor with a healing touch, resolve the problem. Foundation distress. Now look at my friend, he's in great distress here, hanging from the branch of a tree, which seems very dangerous. So this kind of distress could be man-made or natural. Um, it could be due to ignorance of soil conditions, poor understanding of foundation behavior, wrong construction practices, misuse or damage of facilities, wrong estimation of loads, cover depth, soil properties, etc. Um, Additional loads are imposed on the foundation without understanding the impact, unusual site conditions and not recognizing the problems that may be involved. Uh, there could be poor construction quality and localized phenomenon like an old pond or a well or something. All this could lead to disaster or casualties. So when we talk about foundation distress, we have settlements, shear failure, and serviceability issues. So settlements could be total settlement or differential settlement. And in serviceability, we could be talking of excessive settlement or a lower factor of safety or displacements which are not acceptable. Basically, the approach is the same as forensic, preferably without involving the court of law. So the legal system here is the basis, but if we can bypass the law, the court, the problems could be solved much easily by the engineers. So to mitigate distress, you want to ensure that the desired factor of safety is achieved. You meet the serviceability criteria. Restrict further distress or settlement. If some settlement might have taken place, you want to make sure that there is no further settlement. You may want to allow additional loads. The structure may have to carry additional loads. Maybe there is a vertical expansion or additional kind of stresses coming on the foundation. And to facilitate adjoining constructions, make sure that there is no disturbance to the adjoining construction. So if you will look at mitigating distress, what you are looking at it is you want to know the geology of the area and the soil details, the foundation details. Select of the adequate correct techniques for investigation. What kind of tests need to be done? Perform these tests and then assess the reasons for failure, the nature of distress. Select your design profile and do your analysis to assess how this problem can be solved. So ideally, to mitigate distress, you would want to take steps before the disaster strikes or on noticing the first signs of failure. Take preventive actions to avoid the failure. An experienced engineer can identify telltale signs of potential failure and he can suggest remedial measures. If they are implemented in a timely manner, the failure can be avoided or at least minimize the impact of the failure. Various foundation strengthening measures are available. Just giving a brief list, there are many more. So you may want to improve the soil strength characteristics. You could go for stone columns or other ground improvement techniques. Engineer the supporting foundation by retrofitting or micropiles. Confinement of foundations may be done to restrict the settlement and to increase the shear resistance. Restrict lateral soil movement by grouting or contiguous piles. Why distress occurred? This is something which we have to understand. If there is an actual failure, we may be able to work out, back calculate the soil parameters. So then you can do your design accordingly. If there is a partial distress or a serviceability problem, you may not be able to do the back analysis it requires the ingenuity of the engineer. A potential failure, no failure yet, but it is likely. That kind of a scenario may be when the factor of safety is insufficient, or you have an unreliable foundation. You have to rely on the available geotechnical data, boreholes, field tests, and lab tests, and try to figure out if something is likely to happen. So we need effective solutions in all these cases that can be implemented easily within a short time span with locally available technologies that are cost effective. What went wrong, where, and why? These are the 4 W's of forensics. So the 4 W's is what guides any forensic investigation. What went wrong, where, and why. The 4 W's are the key to understanding the problem and developing an appropriate solution. This can guide you towards a solution. You assess the likely foundation system required to ensure that the foundation is safe. This is the investigative part of forensics. When we talk about forensic geotechnics, we are investigating the reason why the failure occurred or is likely to occur. It involves a scientific approach. Understanding of the soil behavior is most important, and then evaluating the structural response, the structure response, soil structure interaction. Understanding what triggered or caused failure, why failure occurred, can provide an insight to the type of restoration that is required. Just give you a few examples of failures, geotechnical failures. So this is the Bhuj earthquake, which caused a lot of damage in Gujarat. This is a hill slope failure. A tunnel beneath a site we had identified here in Delhi. A timely identification of the cavity beneath the site avoided a major disaster. The famous Leaning Tower of Pisa is a classical example where the structure is still standing. The main problem is the serviceability. There is still no damage, and various techniques have been used to stabilize the tower and keep it at the same angle without further distress. Qutub Minar has also undergone some tilting, and some grouting has been done below the foundations to restrict further total and differential settlement. This is the 1,000-pillar temple at Warangal in Andhra Pradesh. Some of the foundations of the 1,000-pillar temple built by the Kakatiya dynasty in Warangal has experienced distress. Stone columns were installed to strengthen the foundations, provide confinement, and restrict further movement. Now I shall be presenting 3 case studies to demonstrate the application of the principles of forensic geotechnics, primarily the 4W, to understand how when there is a failure, we can approach the problem and resolve it. So the first case study, this is a site in Bahadurgarh in Haryana, failure of piles for a tire factory. So this is the location of the project site. It was a rubber tire manufacturing facility in Bahadurgarh. Steel pre-engineered buildings were under construction. Board piles of 600 mm diameter, extending to 16-meter depth, were installed. Each pile was designed for a vertical compression of 50 tons, and 2 piles were provided below each pile cap. During the erection of the steel structure for the pre-engineered building, settlement was observed in some of the pile caps. The measured settlements were more than 50 to 100 mm in some places. Substantial settlement was observed in the pile cap at grid BB18. That was the location where maximum settlement was observed. So this is the BB18 foundation. So at BB19 also there was some distress. So pile number 238 and 239 were in BB18, 236 and 237 were there in. So a detailed investigation program was developed. So this is the BB18 for the investigating the failure. We'll get back to you. I'll explain this what we did. So the forensic post-failure study was undertaken to find out the underlying cause of the settlement prior to suggesting remedial measures. So the investigation was done in 3 phases. One was a detailed geotechnical investigation to assess the stratigraphy. This included boreholes and static cone penetration tests. Then we did some non-destructive tests. This was the low strain pile integrity test, PIT, to identify defects in the piles, and parallel seismic tests to assess the pile length. Then we did some concrete coring to evaluate the continuity of the concrete in the pile and to assess its quality for the clinching evidence of the defects. So this was the scope of work in BB18, 238 and 239. Borehole, static cone penetration test, pile integrity test, parallel seismic test, and pile coring was done in both these piles. BB19, we did most of these other tests except, of course, the pile coring, because these piles were found to be, we could assess the problem there. And the other pile caps, boreholes and static cone penetration tests were done to maximum investigation, of course, in grid BB18, where the maximum distress was observed. So this is geotechnical investigation, the boreholes in progress here, and the static cone penetration test being done. The typical borehole data, this is it's a part of the Indo-Gangetic alluvium. So what we were getting is sandy silts to 9 to 12 meter depth. And then we had sand layers below that, and then again sandy silt. What is of main concern is that the if you look at the SPT values here, very low SPT values, 4 to 6 in this borehole. Similarly, low values in this particular borehole. This one had a lot of loose soils down to about 14 meter depth, and this other borehole, this also in BB18, this showed me very low SPT values, as low as 1 in up to about 14 meter depth. So that was the strata condition. Similar profile in the static cone penetration test. Few of the tests showed me very low results of cone tip resistance up to 14, 15 meter depth. Mostly up to 12 meters it was showing low in BB18 and BB19. Now I come to the 4W assessment of the problem here. So number 1, it is clear that loose soil is observed in vicinity of BB 18 and 19. 2 theories were put forward that in situ conditions were varying. It was unlikely in this area. Migration of fines caused by improperly designed well point system located at a distance of about 10 to 15 meters. This seemed to be the most likely case why the soil up to 14, 15 meters was loose, because of the migration of fines and low SPT values, whereas the other boreholes were showing better results. It is clear that the pile settlement was triggered by the reduced geotechnical capacity in these loose zones. We then proceeded to check and verify the structural integrity of these piles. First, what we had done was low strain pile integrity test. So excavation was done to expose the side of the pile below the pile cap. So we tried to expose the pile here, and low strain pile integrity test was done by impacting the pile on this side. So later the pile cap was dismantled and the test was repeated from the pile top. Here you can see the low strain pile integrity test, in which a handheld hammer is hit on the top of the pile, and then you can get the response on the PIT system. The wave can then be analyzed to assess what the problem was. So I look at this is a pile of from P238 and PB 18. We found there was absolutely no toe response. There seemed to be no when we impacted it from this side, and when we impacted it from the top, again what we got was a weak toe. So it obviously means that there's some problem with the pile tip. So this is the summary of the results. So when we were 238, the one pile, poor data shows that result is inconclusive. Obviously, the quality of the data was inconclusive because the pile concrete quality was poor, and there was hardly any toe. There was a strong reflection at 3 to 4 meter depth, indicating a major defect at 3 to 4 meter depth. In 239, the data indicates that either there is a defect at 6 meter depth or the wave could not penetrate below this level. You can see all these tests, the conclusions are after so many tests were repeatedly done on the piles, so that, you know, we just made sure that there is no error. 239, this one showed weak toe reflection at the anticipated pile tip level. And when we dismantled the pile cap, we could get a reflection at 3.5 meter depth. This showed that, you know, this could be due to bulging of the pile. So the PIT data did not match the expected trends, suggesting that there are possible defects. Both the piles, pile caps exhibited strong reflections at 3 to 5 meter depth, which masked the deeper data. In pile 238, there was a major defect of necking or soil inclusions at 3 to 4 meter depth. In 239, there was bulging at 3 to 4 meter depth, and probably collapse of the loose sand occurred during the pile boring. Pile contractor, I'm not sure whether they used a liner or not, but the bore has collapsed there. The pile length may more or less be okay, but the data is uncertain. Then we suggested to physically excavate and verify to about 3-4 meter depth, but the owners were skeptical. We eventually opted to install additional piles and move on. But then we did the further investigation by what is known as the parallel seismic test. So this was the pile cap, and a bore of 150 mm diameter. It was done to about 30 meter depth, or 14 meter below the anticipated pile level, at a distance of about 1-2 meters from the pile. The borehole was cased with a 3-inch PVC casing and grouted with a cement bentonite mix, so that we have a stable hole. And the pile cap was impacted using a hammer, Teflon tipped hammer, and geophones were lowered into the hole, and the response was recorded. Readings were taken at every 1 meter depth interval. So the concept is that you look for changes in the arrival time of the wave at the geophone location. The software computes the wave velocity based on the traveled time, distance, and the arrival time. The diffraction or change of slope occurs as a result of the pile tip acting as a point diffractor and a reflector. So there are changes in the wave velocity indicates the pile tip level. So the wave would be traveling in soil rather than pile in concrete. This is a picture of the parallel seismic test being done here. This is the pipe installed in adjacent to the pile cap, and the geophone being lowered into the hole here. So you can see the break which is occurring in the wave velocities, P wave velocities. 238, it did not show any change of slope. This means it's a bad pile. At 239 pile, this showed a change of slope at 13 to 14 meter depth. So we should have expected 16 meter long pile. So this is probably a short pile. 236 and 237, these showed nearly 16 meter long pile. So this seems to be okay. So the key findings are that the data quality at P238 is poor, probably due to the presence of loose soils or structural defects in the concrete. 239 actually indicated shorter piles. At BB19, the pile lengths were okay. Next, we went to coring through the pile. The objective was to confirm the structural quality and integrity, continuity of the, so that you can confirm the findings of the PIT and parallel seismic test. So hydraulic core rotary drilling was done with a double tube core barrel, 32 carat diamond impregnated bit to maximize core recovery and to minimize the mechanical fractures. So this is the core concrete coring in pile 239. You can see here fractured core, and then soil and weak concrete was encountered below 12.5 meters. This is the picture of the coring and RQD quality. So in this pile 238, in fact, we entered soil at 5.67 meters. So this gave the question that probably the pile is bent or damaged. There's no pile below 5.67. Pile 239, 12.5 meter was the concrete, and then it was showing soil below. So this is the summary of those results, the coring observations. Bent reinforcement pieces were found in the last core run, and the pile was probably inclined and possibly damaged. Soil was encountered below 5.67. In the other pile, of course, core recovery dropped significantly due to the weak discontinuous core, and at 12.5 meter nil core recovery. The color of the return water was gray, indicating that we are still drilling through concrete, not soil. Probably weak concrete or slush, maybe intermixed with soil. So there was some reinforcement also we met at 14-15 meter depth, either due to bending or of the pile bore, or maybe it got damaged a bit. But there were issues. So the conclusions was that the geotechnical investigation revealed these loose soil zones, and 238 was damaged and discarded. 239, its capacity was reduced due to poor bottom cleaning. Additional piles were installed at BB 1918 location, and similar kind of approach was used for BB 19. The study successfully investigated the root cause of the failures, thus paving the way for remediation. I now come to another case study This is an overhead tank on loose boulder fill in Gwalior in Madhya Pradesh. So an 18-meter overhead tank close to an existing school was planned. It was located in a congested area of Gwalior near the famous Gwalior fort. So the site is near the what is called the Killa Gate, heterogeneous loose fill of stones and boulders, probably discarded by the construction during the construction of the fort, 15th century fort built by Man Singh Tomar. So it had a fill to about 7-meter depth. The owner and structural designer did not have any clarity on how to design the foundation for the overhead tank. The result was an unsafe and unreliable design. Routine geotechnical investigation was done. The standard specifications for geotechnical investigation said that borehole to 15-meter depth or refusal, whichever is earlier. So refusal was to the SPT was encountered at the ground level itself on the boulder fill. So obviously no data was collected. The structural designer then suggested to do a plate load test. And the plate load test was done on a 13 to 30 centimeter size test plate. The measured settlement was very small. So the designer thought that using an SBC of 150 kilonewton per meter square is conservative. And as a result, what he designed was a 23-meter diameter RCC raft foundation at 2-meter depth. Then they started the excavation. When they did the excavation to 2-meter depth, they found boulders. And when they found boulders, they started excavating further. And they did the excavation to 4-meter depth. At 4-meter depth also, a heterogeneous mix of stones and boulders in a sand matrix was met. The contractor panicked. The owner was concerned that the strata may not be a suitable bearing material. So at that time, the client requested IIT Delhi and Cengrs to evaluate the conditions and suggest a solution. The site conditions, this is how it looked like at that 4-meter depth excavation. Stones and gravel and boulders in a sand matrix. Some of the stones may be part of the stone masonry construction. Binding material probably got eroded with time or probably got weathered, and loose pockets were observed in the fill. Several of the buildings were constructed adjacent to the very bad condition, dilapidated condition. And excavation has been carried out very close to these buildings and nearly steep excavation. Surprisingly, they were still stable. So this is a loose stone fill here on which the building has been constructed, and you can see the condition of that building. At places, the foundation has also been exposed. So an attempt has been made to give some lateral support by stacking material against the wall of the building, but mostly it is inadequate. So this is the site conditions. The concern was the safety of a school building adjacent to the excavation. So a cement mortar was used to stabilize some of those stones. Obviously, it's a very poor effort. They just applied some cement mortar, and it seemed they thought that they had done a great job there. Now I look at the 4 Ws for this case. Such overhead tanks are usually designed as per standard drawings based on a so-called conservative foundation design with limited assessment of soil conditions. The structural engineer controls the design. The geotechnical engineer's input is limited or non-existent. There is a very poor understanding of this strata behavior. There is a lack of application of uncertainty in behavior of the loose heterogeneous boulders, and the type of investigation method that should be adopted to assess the problems here. Since the contract had been awarded, the approved budget cannot be exceeded was the another issue. So an engineering assessment showed that the fill extended to 7 to 8 meter depth. Being loose and heterogeneous, it is not a reliable foundation bearing material, not suitable at all. And the available geotechnical data is insufficient. No realistic data is there. Results of 30 into 30 centimeter size test plate load test cannot be extrapolated for the design of a 23-meter diameter raft. No clear conclusion can be drawn. Evidently, it is not feasible to support the foundations on the boulder fill. So the action plan was first perform a proper geotechnical investigation with at least 4 boreholes extending to at least 20 meters beyond the bottom of the fill. So we did the boreholes up to the 20 plus the 7-8 meters of filling. SPT and undisturbed samples were collected and a complete range of laboratory testing was performed. So we had to excavate to the bottom of the fill zone and then erect a platform and then do the boreholes. Although the safety of the adjoining building was a big concern, no failure had been reported. The typical borehole data below the 4-meter level, we did another 2 to 3 meters of filling was met, so making it around 7 meters. And below that, we got the natural soils was clay silt of medium plasticity. It is not expansive. It's an alluvium, extends to more than 23 meters below the excavated level. And the SPT values are about 10 to 15 to 2-meter depth below the fill. And below that, the SPT values are gradually increasing with depth, goes up to 50 to at 15-meter depth and further increases to more than 80 to 100 at 23 meters. Groundwater was interestingly not met to the final explored depth of 23 meters. The soil properties which we had determined in the laboratory showing that it's a medium plastic clay with a plasticity index of 11 to 29, very low free swell index. Of course, very little gravel, and then the clay content was around 16 to 36%. And the undrained shear strength properties, you can see here 7 to 10 meter depth, 100 to 140 kilonewtons, and then 10 to 23 meter depth, you had much higher values. So the engineering solution for the overhead tank was that the fill is loose, heterogeneous, and unreliable. It is not suitable foundation bearing material. The foundations for the overhead tank should bear on the natural soils below the fill. Restricting the total settlement to 50 mm, although you could go up to 75 mm. We propose that the safe bearing pressure can be around 225 kilonewtons per meter square. Accordingly, the raft diameter was reduced from 23 meters to 18.5 meters. This not only saves on cost, but also reduces the excavation size and to avoid getting close to the adjoining buildings. So there is a little safety there. So further excavation to 3.5 meters below the excavated level is required, and the foundation has to be constructed on the natural soils underlying the fill. The risks here is that excavation needs to be monitored since it is very close to the existing building. So some of those buildings are in quite bad shape, and some building foundations are already exposed. The excavation is marginally safe, so the lateral support system which has to be provided depends on the extent of risk that the owner is prepared to take. So the excavation may be done in localized stretches with temporary support to the excavation in small stretches. Somewhat risky but economical, so worth taking. Can take a chance if the construction is done before the monsoon, and there was quite a lot of time before the monsoon, so they could do that. Shortcreting the excavation phase shall enhance the stability during the construction period, not the sketchy cement slurry which they had placed. Diaphragm wall, of course, was a continuous, was a reliable system, but it's a very high cost, makes the project financially unviable. So I come to the last case study. This was a deep excavation for a multi-story building in Gurgaon, in Haryana. The project details is that it's a 16-meter deep excavation for a building adjacent to a 6-story building. The building outer line is about 6 meters away from the edge of the basement, edge of the excavation. And the basement of the existing wall extends to about 5-meter depth below existing ground level. After heavy rains, part of the boundary wall of the existing building collapsed, and boundary wall was at a distance of less than half a meter from the edge of the excavation. A soil wedge fell along with the boundary wall. So this is the existing building here, and this is the portion of the wall that collapsed, and this is a deep excavation that had been done. So that's a view of the, so that is that existing building, and we had dismantled the collapsed portion of the boundary wall. Nearly vertical cuts to this at this site have been observed to be stable even to 16-meter depth. This soil is silt here. The erosion due to rain caused instability. The boundary wall is too close to the edge of the excavation. The exposed soils beneath the boundary wall got saturated during the rains, and this resulted in development of a slip circle, which caused failure. The building owners feared that the soils adjacent to the excavation may progressively collapse and endanger the safety of their structure. Therefore, it was necessary to protect the building so that it remains safe even if there is any further collapse of the soils. The main problem was that the neighbors were panicking. So we did some boreholes, and this is what it showed, that except for the top loose soil to about 1 meter depth, the soil seems to be quite good, sandy silt here. These are the soil properties, and cone penetration test also showed that below about 2 meters the soil is good, gradually increasing with depth. No water table to 20-meter depth. The soil is alluvium, Delhi silt of low plasticity. Maximum 2 to 2.5 meters was used, and SPT and cone tip resistances below 2.5 meter depth is quite good, and below 6 meter depth soil is hard and compact. Now the 4 Ws. The building appears to be safe in its present condition. To ensure the safety of the building during the entire construction period, precautionary measures had to be taken, primarily to convince the neighbor that it will remain safe. Possibility of further collapse of the soil needs to be arrested. So the proposed lateral support, which was done, was the cement grouting of the soils adjacent to the existing building. It was a time-saving and cost-saving effective solution, cost-effective. Grouting at closely spaced points can effectively create a grout curtain. This can provide sufficient lateral support of the soils adjacent to the building. So this is the approach that we had used. This was the borehole which was drilled, and a conduit pipe, and the conduit pipe was plugged at the ground level and at the basement of the building, and the 75 mm diameter hole was plugged at basement level, and cement slurry was pumped. So the grout consisted of 50 kg or one bag of cement in 100 liters of water at a pressure of 0.5 to 1 kg per centimeter square, gradually increased to 2 kg per centimeter square. The injection of the cement slurry was continued until refusal to further grout intake was met under a steady pressure of 2 kg per centimeter square. The cement slurry was agitated continuously during the process, during the pumping. So two rows of grout holes were drilled adjacent to the excavation, adjoining the basement line of the existing building in a stretch close to the excavation. Along each row, the spacing was kept around 1 meter, center to center. So this is the scheme here. This side is the excavation. So we had 2 rows of grout holes. Total 84 points were grouted. Average cement consumption was 2.5 to 3.5 kg of cement per hole. It could be completed in about 2 weeks' time. Substantial saving in time and cost in comparison to contiguous piles or sheet piles, etc. So these numbers here, they are the number of bags of cement that went in. So this is the completed retaining wall after the grouting was done. And the new boundary wall being constructed on top of the afterwards. So the boundary wall was supported on 300 mm dia, 10 meter deep auger piles adjacent to the boundary wall, a basement wall. So now I come to the lessons learned. Geotechnical distress mitigation is one step before the court of law is involved, if at all possible. Try to resolve it mutually. It's not a fault-finding mission, but a fact-finding mission. The purpose is to save the structures from major disaster and damages. So forensic geotechnical engineer should be a doctor with a healing touch. The 4 W's, these are the key to the mitigation of foundation distress. You have to have a scientific approach with an open mind, evaluate the surface substrata behavior, predict the behavior of the structure, assess why foundation failure occurred or why it is likely to occur, work out the engineering solution, implement the foundation strengthening scheme, monitor the effectiveness. Forensic geotechnics is as much an art as it is a science. Detailed investigation to the causes and mode of failure, developing engineering solution for the failure or potential disaster. Everything needs sound engineering practice. Thank you for your kind attention. I'll be happy to take questions. Thank you.
Thank you very much, sir, for this enlightening session. I think we should learn from the failure of others rather than getting into our own failure and then.
Very true.
Getting people in a situation where they are at risk. So definitely. In fact, I have also worked with one of my PhD scholars, and we worked on some of the issues because he was from the field. So he came to me and then discussed that we have constructed around 15 Hume pipes, and out of 15, 13 were showing the same kind of damages, same pattern of damages at the ground. Okay. So we started investigating, and then we found a lot of challenges are there. Like I don't know why it is there. But then it is observed that it has become the culture of it has become the culture, and like it starts from material selection to insufficient geotechnical investigation to casual approach contractor. Like they will say that okay, chalta hai, kind of approach.
But the chalta hai approach is the biggest problem.
And then lack of knowledge, information. Then they rush to complete. They will be sleeping for 15 days and then suddenly they will wake up and then they will think that overnight they can construct everything. So these are the challenges. These cultures should be actually, and this can only be controlled through these kind of investigation, because if they are aware that if some failure occurs, then definitely there will be investigation and they will be asked for the purpose. So then only things can be done. And then we have a scientific approach for that now. We know step by step how to proceed and how to fix the liabilities on either contractor or designer or whoever is involved. They are the stakeholders, and then they should be responsible. So with that, I very much thankful to you for spending time with us and sharing a lot of case studies and field studies that must be motivated to future researchers, scholars, and students. And now I request. So before that, I will just see the question is there. There is a question from Singham Jayantu sir regarding case study 3. Maybe know how the adjacent excavation was made.
About calibration of the sensors.
Yeah, yeah. I think you can also read the question from your side.
Singham has asked me that to throw some light on the calibration of sensors used for the tests, like the geophones. Well, the geophones that we use was the triaxial type, and we were getting it calibrated. This equipment was imported from U.S. Olson, so we were getting it calibrated from them regularly. So as such, I have no personal experience with calibrating these sensors. I'm sorry about that. Case study 3, you had asked me something.
If it is convenient, I can also.
How the adjacent excavation was made? Oh no, it was just made with a regular excavator because there was no blasting. It was all soil, and there was no need for any blasting. So they did it with a regular JCB type of excavator, and they were all very happy. Nothing happened because it was when they did it in the dry season, it was quite stable. But during the monsoons, they realized that the part of the boundary wall failed, and it was not very critical because just the boundary wall had failed. But then it was the neighbor who created a issue and said that there could be progressive failure and it could get close to my basement. So therefore they were concerned. They had to do that.
So thank you very much, Professor Sundaram sir. Are you able to hear my voice?
Yes, sir. I am not.
In fact, I was doing around 30-35 years research to CSIR as well as Ministry of Mines, conducting studies on this effect of blasting, especially on the structures, as well as underground excavations also, and slope stability. So of course that I will be discussing during 28th. I think our Amit Saab has given me that time. There I will be explaining our works. So that's why I got a doubt, Sundaram Saab, when you presented that up to 16 meters there is a failure slip surface like that. Then that might have triggered because of somewhere there may be some blasting, and that might have triggered this failure, something like that. I got a doubt in that way.
So 28th is your presentation. I will definitely attend.
And regarding instrumentation, that is very, very important aspect because I have my PhD scholars from transdisciplinary group. You must be seeing in my board, I have been preparing one new document on National Education Policy 2020, vis-a-vis our mining education. So there I started in 2006 itself, our transdisciplinary groups with electronics, computer science, instrumentation, all those people, sir. That's why I wanted to know, because I've been using many types of ground control instrumentation, since 1989 as a scientist in CSIR, and over 100 projects I completed. And I have a very bad experience with many instruments, not to name any manufacturer or anybody. That's why I wanted to know, before using any instrument by our beloved geotechnical engineers, they should ensure that that is properly calibrated, and they should know about it. They should know about it. That is very important. That's why I wanted to
very true. Unfortunately, the present industry scenario,
Yes.
nobody is prepared to spend on instrumentation.
That's right. But it is very much required for our rock mechanics, because it is all observational approaches. We don't believe in numerical modeling or analytical equations like our, if it comes to our rock mechanics and other, starting from our mining side, if I say, Professor S.S. Peng, Fairhurst, and other people, even our Nick Barton, who was a very good friend of me, we used to conduct in collaboration many projects. And from Rock Mechanics Technology UK, we were doing international collaborative projects also. Rock Mechanics Technology UK, and then Norwegian Geotechnical Institute, Norway, where Dr. Nick Barton, who was the originator of our rock mass quality, I mean Q classification. So we were giving so many courses that anyway I will be discussing on 28th.
Yes, sir, we are waiting. We are waiting for your session on 28th.
Yes, I am very much thankful to our Dr. Amit Srivastav sir for giving the right platform to share some of our experiences.
Yes,
We believe our knowledge flow like a river water.
We want to listen from you, sir.
Yes, Dr. Amit has been very proactive in making sure that geotechnical engineering doesn't remain inside the universities. It comes out into practice.
Yes, sir.
We have to collaborate. All industry experts should collaborate with the academic people, and then only it is possible. Because young generation will learn from the experience, from the academic viewpoint. Also, they should understand the importance of certain things. Like I know many of my students that they missed the class of compaction, and then they realized that how important this topic was, because when they start looking at failures at the site, I missed compaction class during my BTech. So that is the reason. So that connect should be there. That connect should be there. So I once again thank you, sir. Ravi Sundaram, sir. Because of limitation of time, I have another class now at 3 p.m. So I will request Salonia to give vote of thanks and certificate of appreciation to our expert who has joined with us. Over to Salonia.
Yes, sir. Thank you very much, sir. Thank you very much, Ravi Sundaram, sir, for taking up the queries of our audience. And on behalf of Lovely Professional University and from the entire team of faculty members and students at School of Civil Engineering, including IBS Jalandhar chapter and Department of Civil Engineering NIT Jalandhar, I'm thankful to you for spending your time with us. We wish you all the good health and prosperous life ahead. As a token of appreciation, please accept our e-certificate of appreciation. Thank you once again.
Thank you, Salonia, and thank you, Professor Amit Srivastav. I'm honored to receive this certificate. Great to interact with all of you. I see one or two other questions, which probably I can respond later on by email.
Sure. So hope you were able to see your e-certificate of appreciation.
Yes, I have seen it.
That's great. That's great. So thank you once again. Thank you everyone for joining with us. Thanks a lot.
Okay. Namaste, sir.
Thank you. Namaste.
Jai Hind.
Jai Hind.